Okay, so last time we met, we were working on these ionic equations. And it's important to recognize that when we see something written like this, sodium carbonate, aqueous, reacting with calcium chloride, aqueous, forming calcium carbonate solid and sodium chloride aqueous, two sodium chloride aqueuses, it's important that we recognize what's really occurring. And that means that because this is aqueous, there's no sodium carbonate. It's really two sodium ions and one carbonate ion. And there's no calcium chloride. It's really one calcium ion and the two there showing us that we have two of these chloride ions. All right? And so we can write ourselves an ionic equation that kind of more specifically shows the ions that are involved in the equation, like we did for this one up here. We wrote out our compounds that were aqueous as the ions that they were. If the compound is solid, we don't write it as aqueous, we write it as solid. Like we did here, lead chloride stayed solid in the ionic equation. All right, so let's see what we can do. Okay, let's write out our ionic equation. What do you think? Do you think that you can tell me what's supposed to be included in this ionic equation here? If I want to write the ionic equation for this chemical reaction here, what should I start off with?
Let's see. So
what are our
two?
Yeah, two what?
Two Na.
Very good. Two sodium ions. What's the charge on the sodium ion?
Yeah.
That is element 11.
I get my chart.
Element 11.
Yes. Minus 3? No, that's nitrogen. Sodium ion.
Element 11.
Thank you.
Very good.
Yeah, plus one.
Good. So we got our sodium ions. Now what's next?
And then 3. That's a 3, right? 3.
That's CO3. Can you see that, or no? Is it too small?
Just a little, too small, but would be 3 CO.
Well,
right?
It's a polyatomic ion.
Oh no, I'm sorry. Oh, you're saying that's a poly. Oh, you're saying that's a poly.
CO3 there.
Oh, okay. It has a. Oh, that's a. Okay, it's got a minus 2 charge. Got a minus 2 charge.
And you know what? We could have known that also by recognizing that we're two sodium.
Oh yeah.
Right? Okay, good. Excellent.
Right.
Now, what's next? Calcium chloride breakup.
So we would have. Chloride is the Cl, right?
Yep, Cl minus, right? Has a minus charge on it.
The Cl, right? Okay.
How many chloride ions?
Calcium would have a plus. Okay, and then
a positive what?
Calcium would have a
what's the number on that?
plus charge. That would be a plus 2.
Very good, positive 2. And then
that would be
how many chloride ion? There's.
Oh wait, no, I'm wrong. That would have a minus 2.
It's element 17.
Oh wait, no, I'm wrong on that.
It's on the periodic table. It's just chloride ion.
It's on the back, right?
It's element 17.
Okay, so have a minus charge.
Yes, minus 1. But that 2 down there tells me that I have 2 of them, right? 2 of the chloride ions. Okay. What do I do with the calcium carbonate now? Do I break that up?
Right.
It's solid, right?
Yeah.
So it doesn't break up. CaCO3. It's not
yeah.
aqueous, insoluble. So I just put that directly how it is. Okay, very good. What's
okay, and then
very good. 2 sodiums.
the 2Na. And then the 2Cl.
Very good.
2Cl are
2Cl minus. Excellent.
2Cl negative.
That's right.
charge.
Sodium ion and the chloride ion are our
And so
spectator ion.
Those two are
And
our
if we wanted to go
spectator.
from the ionic equation, which we on here, to the net ionic equation, we would get rid of the spectator ions. Very good. And that's what this next problem does. We start this time with ionic equations, and we try to identify the spectator ions that we need to get rid of to go from the ionic equation to the net ionic equation. All right, so what do you think? What are our spectator ions in the first equation here?
It would be the 2NO.
Very good. The 2 nitrates.
It would be the 2NO.
Yes, potassium. 2 potassium ions.
And the 2
Excellent.
case
Good job.
potassium, right?
And whatever's left over is what we call our net ionic equation.
Right.
Excellent.
So, I'm processing this the long way, right?
Yeah.
So, I'm processing this the long way, right? Can I just look for the solid and
Yep.
and then
That's fine as well.
chances are it's going to be what's left over from the solids, the spectators?
No, that's usually right. If it's in the solid,
Is that
then
usually
the
a
chemistry
given,
is,
or do I have to
the
double
solid
check?
is where the chemistry, the product from the chemistry is going to be if it's a precipitation reaction, right? Okay, very good. So here's a couple more. We'll let the folks at home work on those, and then we'll show them the answer here pretty
Right.
quick. So work on these if you're at home, and then I'll
Okay.
show you the answer in 2 seconds. So go ahead. 1, 2. All right. Push pause if you haven't had a chance to finish. So identifying the spectator ions and the resulting equation there is how we get to our net ionic equation from the ionic equation. Okay, very good. Now we're going to introduce a new class of chemical. And this class of chemical comes from in the molecular compounds. So remember, we kind of initially, we said all of our compounds kind of can be comprised into molecular or ionic. Remember this business? And our molecular compounds were compounds that were made of non-metals, molecular compounds. Ionic compounds, we have a better definition now. We call it a compound that is made of ions, but if it contains a metal, then we know it's an ionic compound. All right. Now I'm going to teach about a new kind of compound. It's within the molecular compounds, so they're made of nonmetals, but they behave like ionic compounds do when they're placed in water. That means that when you put them into water, they dissociate, they separate. All right? Now, molecular compounds generally don't do that, but there is a group of molecular compounds that do. And when they dissociate, one of the products is the hydrogen ion, or H+. And these compounds are called acids. So acids are compounds that are molecular compounds, but when you put them into water, they dissociate. They dissociate. So here's our chemical equation. HCl, that's an example of an acid. It goes into water, and then it separates into an H plus ion and a Cl minus ion. Okay? So, acids dissociate when they're placed in water, and one of the dissociative products is always the H plus ion. Okay? Now let's talk about what that H plus ion does when it dissociates into water. A water molecule, when it's introduced to an H plus ion, let's do a quick review. Let's go back a little bit and look at what happens when we put sodium chloride into water. Do you remember what happens when we put sodium chloride into water?
Yeah, well, like you said earlier, right? The H will
Sodium chloride crystals.
Yeah,
Okay, so here it is. So the sodium
Well, like you
chloride,
said
when placed into
earlier,
water,
right? The
our three-dimensional
will
lattice
Sodium
is
separate
torn
chloride
apart,
crystals are
right?
from the chloride.
Because the water molecules, they grab on to the ions. Here the hydrogen end, and here the oxygen ends are grabbing the sodium ion, because the oxygens have a negative charge associated with them, and the sodium has a positive charge. So the sodium ions and the chloride ions dissociate from each other, right? And that's what we've been talking about. We've been talking about, for example, NaCl going into water, dissociating into sodium ions and chloride ions. And these are AQ, dissolved in water, surrounded by water molecules. Well, the same thing happens when we put an acid into water. The H plus is surrounded by the oxygens of water molecules. So here are some water molecules I'm drawing. And they actually will pick it up. So a water molecule will temporarily have 3 hydrogens and get a positive charge. And this is the polyatomic ion that's on the top of your chart, the H3O plus ion. This polyatomic ion, though, is short-lived, because as soon as that happens, a neighboring water molecule comes along and will pull that third hydrogen off and will become H3O itself. So a new bond will form here, and this bond will break. Right? And it happens really fast. And as soon as that H3O forms, another water molecule that's nearby will form a bond with that hydrogen, and this one will break. So essentially, the hydrogen ion is not in one place. It's constantly moving, kind of like an electron in a piece of metal, constantly moving from one place to another. You'd never be able to really locate it in the water. It just is bouncing off. So it could be here, bounce through the water molecule, and then show up over there, right? Because it's just being passed from person to person. Did you ever play that game, Ring on a String? Everybody...
No.
Everybody is in a circle, and there's a string, and everybody's holding on to the string, and there's one ring. And you can pass the ring, and it goes really fast around as people pass the ring. And the person in the middle is looking and trying to find who has the ring, right? It's a fun game, but it reminds me of this, how the hydrogen, the extra hydrogen, is just moving all around, and it can go either way, back and forth, and it can move pretty fast if you wanted to. Okay. So, because of that, some people like to write the acid dissociation with the water molecule present. Okay, so let's get back here to the acid dissociation. So just like we wrote that we can say HCl, which is a molecular compound, all nonmetals, but because it's an acid, and another way we can recognize an acid is that you will usually have a hydrogen first. HCl, because it's an acid, it dissociates when placed into water. To write this, I am personally not a fan, but people like to write it like this, where they say HCl interacts with a water molecule. And then that water molecule picks up a hydrogen from the HCl and forms H3O plus and leaves behind the chloride ion. So we have two different ways of writing our dissociation of our acid. Okay, the dissociation of our acid. Okay, very good. Can you see the differences here? One has the water molecule that picks up the hydrogen, and one just shows the hydrogen by itself. But both of these are indicated as aqueous, so they're both surrounded. All the ions here are surrounded by water molecules. All right, here is another acid, HC2H3O2. HC2H3O2. That acid is called acetic acid, and acetic acid is an example of an acid that when you place it into water, it dissociates, a hydrogen ion comes off and leaves behind the... But in this case, the hydrogen ion, or the, let's see, in this case, oh yes, the hydrogen ion doesn't like to come off of the acetate ion. And as soon as it comes off, it will go right back on very quickly. And so what we have here is what we call a reversible reaction. This acetic acid is what it's called, dissociates and then back and forth very quickly. And because of this, this acid is what we call a weak acid. Weak, which means it doesn't dissociate very much. So maybe 1 in every 10,000 acetic acid molecules will be dissociated at a time. So compared to HCl, which is a strong acid, you put HCl into water, and because it's a strong acid, that means that it completely dissociates. 100% of the HCl separates into its ions. So strong acid doesn't mean it's strong, it'll hurt your eyes, it'll do this, right? It just means that it's completely dissociated when it's in water. A weak acid doesn't completely dissociate, it only dissociates some of the molecules at a time. Okay. We also have a chemical that's called a base. It is a chemical that, like the acid, is a chemical that you put it into water, and the hydrogen. Now let's see why that's the case. Again, here's a general example of some acid. Here's my acid, HX. If this is an acid, what will my resulting ions be if I put my acid HX into water?
H plus X.
H plus ion. And then I'm going to get
Plus, minus.
with a minus charge. That's right. So that's the dissociation of an acid. So an acid is a molecular compound that you put into water and a hydrogen ion results. Well, a base is a compound that you put into water, and instead of the hydrogen ion, the other half of the water molecule that's
H
left
plus
over,
X.
which is the hydroxide ion, will result. So that is
Then
what
plus
a base is.
all X minus.
Right? An acid, you put it into water, and the hydrogen ion results. A base, you put it into water, and the hydroxide ion results. And hopefully you can visualize how the hydroxide ion and the hydrogen ion can come together. They can form a bond and form water, right? The hydrogen ion and the hydroxide ion are just two parts of a water molecule that have been broken up. Okay? Now, yeah. Sure. So how do we get the hydroxide ion to result? Well, there's a couple of ways. The most common way for a base is you put something, an ionic compound, that is soluble and dissociates in water, like sodium hydroxide. Sodium hydroxide, we can look at our solubility rules, and the solubility rules will tell us that all compounds containing sodium are soluble. Therefore, sodium hydroxide into water, and you get the hydrogen and the sodium ion. Okay, very good. So, that's one way to get a hydroxide ion, one way to have a base, to get a soluble hydroxide containing salt and put it into water. The other way you get a base is you have some chemical, like we could call it chemical X, and you combine that chemical X with water. And if X removes a proton from the hydrogen ion from that water, what's left is the hydroxide ion. And so that is another example of our another example of a base, a chemical that you put it into water and the hydroxide ion results. So again, a quick review. Acids are chemicals you put into water and the hydrogen ion results. Bases are chemicals that you put into water and the hydroxide ion results. Okay. Now let's have a reminder of what strong versus weak means in terms of electrolytes, in terms of acids, and now in terms of bases. All right? Do you know the difference between a strong acid and a weak acid?
So the strong acid will
That's right.
dissociate 100%.
And a weak acid does not. Now, do you know the difference between a strong electrolyte and a weak electrolyte?
I don't. I guess it's the same.
It is the same.
I don't. I guess
strong
it's the
electrolyte
same thing.
will dissociate 100%. The weak electrolyte will not. Therefore, a strong base is a chemical that dissociates to produce the hydroxide ion, and a weak base doesn't dissociate to produce the hydroxide ion. Okay? So we have strong and weak acids, electrolytes, bases, but not the strength in that this one will kill Batman, that one won't kill Batman, or the Joker, or whatever it was. It's strength in terms of the amount of dissociation. Okay? All right, so here is another drawing to kind of help us recognize that. HCl is a strong acid. That strong acid combines with water, and all of the H pluses release their hydrogens to water, making the H3O plus ion, and leaving behind all the chloride ions, the Cl minus ions. For this weak acid, this is the acid that's in vinegar. So pickles and sour stuff, a lot of it has, salad dressings, vinegar, right? This compound here interacts with water, but because it's a weak acid, only a very small amount of it will actually dissociate. And so we have to have an arrow showing that when those find each other, they'll come back. Yes, another one will dissociate, but will constantly be in equilibrium with a very small amount dissociated and the rest of it associated. Okay, very good. And in terms of electrolytes, strong acids are also strong electrolytes, and weak acids are weak electrolytes. Weak bases, also weak electrolytes. Although weak acids and bases or weak electrolytes will allow a little bit of conductivity to your solution, in general it's not very much compared to strong electrolytes or strong acids or strong bases. Now we're going to talk about naming acids. Naming acids. And there's two kinds of acids that we're going to tell us to kind of categorize our acids into, two different kinds, so that we can remember how to name them better. The first kind of an acid is what we call a binary acid. Binary. Now, do you remember what bi, the prefix bi is? Two. That's right. Binary means two, and binary acids are acids that are made of the hydrogen ion and only one other element, or one other ion, or one other element, okay? So, binary acids, like HCl, now let's see, does your brain, for some reason, know what this acid is called, HCl? Hydrochloric. Where in the world did you learn that from? Do you know?
No, too long ago.
Okay, and that's great.
No, too long
That's great
ago.
because what that does for us is it gives us one acid that we can use as a model to name our other acids. All right? So I'm going to hold you to knowing that that is hydrochloric acid. Okay? HCl. Do you think HCl is a binary acid?
Yes.
It is. That's right. It's a binary acid.
Yes.
Only two kinds of elements, hydrogen and something else. So that is how we name our binary acids. Hydro, we fill in this blank with whatever the ion is there, or the atom, and then we say acid. Or hydroblankic. Hydroblankic. All right? So tell me, what is the name of HBr? Hydro
bromide,
right? Bromic. Very good. Hydroblankic acid. So hydro, and let's write the general formula here. It's hydroblankic acid. Okay? So let's try this one here. HF. Very good. Hydrofluoric acid. Excellent job. Okay, so we're getting it. We're learning how to name binary acids because of our knowledge that we had previously about hydrochloric acid, which is great. And if you didn't know that, now you have to memorize hydrochloric acid so that you can know how to name binary acids. All right. So let's see here. Oops. The other type of acid is called an oxyacid. And it's called an oxyacid because oxyacids contain oxygen. All right. So here is an example of an oxyacid. HNO3. We see the oxygen there, And we also might recognize that the hydrogen ion is with a polyatomic ion. Did you recognize that?
I did not.
Okay. That's another way
not.
we can recognize oxyacids.
I do not.
It's a hydrogen with a polyatomic acid. Okay? And to name oxyacids, we find the polyatomic ion's name. What's the name of that polyatomic ion?
It's nitrate ion.
Nitrate. Very good.
It's
So we
nitrate
find
ion.
the name of the polyatomic ion, nitrate. And then we change 8 to ic. And it's called nitric acid. Okay? Notice that it wasn't called hydronitric acid. The only acids that we named hydroblankic acid are binary acids. But HNO3 is what kind of an acid?
So, how do you say that?
Oxy.
How do you say that? Oxo acid?
Or oxo acid's fine too. Oxo acid. So it's basically just saying oxygen.
Okay.
Contains oxygen.
Oxyacid.
An
Okay.
oxo acid. Very good. So we have oxo acids, oxyacids, and binary acids. The oxygen containing ones we name after the polyatomic ions. If the polyatomic ion ends in 8, then the acid goes to ic. Now, I don't know if you've ever heard of this or seen this acid before. H2SO4, have you ever heard of that before?
That does sound familiar, but that does sound familiar,
I see it
but
on the back here.
All right, what's the SO4
I see it
called?
on the back here.
So it would be, well, the SO4.
So it would be, well,
Sulfate.
the SO4,
So what would
it says
H2SO4
sulfate
be then?
ion.
So hydrogen's sulfur.
So hydrogen.
No hydro. Just like this one
sulfur.
was nitric acid.
Oh, I see. So sulfuric acid.
That's right, sulfuric
Oh, I
acid.
see. So sulfuric acid. Or sulfuric,
Now,
yeah.
Sulfate didn't go to sulfic acid. It threw in the sulfuric. It threw in the UR. But sulfuric acid. Sulfuric acid. All right. So what we learned from naming our oxoacids is that we have 8 going to ic. If the polyatomic ion ends in ite, like HClO3, no, that one doesn't. HClO2, sorry, HClO2. So what is the name of ClO2 ion?
Chloride.
Chlorite. Very good.
What,
If
chloride.
our acid ends in ite, then if our polyatomic ion of the acid ends in ite, then the acid ends in us. So it's OUS, chlorus acid, chlorus acid. All right. H3PO3,
Okay.
the PO3 ion, right? The PO3 2- ion is phosphite, and then the acid's name is phosphite, I guess, isn't on our table. So the phosphite ion goes to us, and it's called phosphorus acid. Phosphorus acid. So this is what we remember, and we put it at the top of our bed so that every time we wake up in the morning, we can see it. 8 goes to ic, ite goes to us. And that's for naming our oxygen acids, right? Okay. So, what do you say? Which one of these should be named following the hydroblankic? Or which one is not named as a hydroblankic acid?
Number C.
C, that's right. How did you know?
Number C.
Well, it's got the oxygen in there.
Very good. It's an oxo
Well,
acid.
it's got the oxygen in there.
Excellent. Okay, so what do you think? What's the name of HNO2? Is it oxo acid or is it binary?
It's
It would be ox.
it would be
Very good.
oxo
Oxo acid.
Or
oxo acid.
Mm-hmm.
Well, or oxy.
So is it named hydroblankic model or after the polyatomic ion?
It would be after the poly.
It would be
Very good. And what is
after
the
the
NO2 ion?
polyatomic
You
ion.
see it there on the chart?
And yeah, so
And
it's not.
yeah,
nitrite,
so
and
Okay.
it would be
it's
changed to
nitrite, and it would be changed to
Very good. Nitrous acid.
Nitrous?
acid. Excellent. How about this one? HClO4.
So that's
So that's
read this, but it's
I'm trying to read this.
Very
but
good.
It's it is an ATE.
Very good. Perchlorate.
Perchlorate,
So 8 goes to what?
perchloric.
and so
That's right.
it would be
Perchloric acid.
perchloric.
Fabulous. How about HF?
So that's binary.
Uh-huh.
So that's binary,
It's
and that's
hydrofluoric.
Very good. Hydrofluoric acid.
hydrofluoric.
Excellent. HMNO4?
Okay, we're back at the back again. That's
Okay, we're back at the back again. That's MnO4 is
Permanganate.
per
Good. Permanganate.
yeah,
ATE, so that's
and so it is an ATE, so that's changed to
IC.
IRS. I mean,
Yeah.
IC.
And
and so that's a
oxyacid.
oxy.
Yeah. Permanganic acid.
oxy.
Very good. Oops, I skipped one there. But that one's carbonic acid. Carbon 8. 8 goes to ic. Carbonic acid. We're going to let the folks do this one at home. You can work on it too, but looks like you already got this under control. HClO3. Okay, so ClO3 ion is the chlor 8. 8 goes to ic, so this is chloric acid. Chloric acid. H2SO3, SO3, pause if you want to work on it. SO3 is the sulfite. Ite goes to us, sulfurous acid. Sulfurous acid. Good. Okay. So we would like to write the ionization of each of the following with water. The ionization of each of the following with water. Okay? And essentially what we're doing here now is we're looking at compounds that are either ionic compounds, and then we want to write their ionization, which we've had lots of practice doing. We're looking at acids, and if it's an acid, we know how to write its dissociation as well. One is the H plus, and the other one is whatever's left with a minus charge. And if it's a strong base, that's just an ionic compound, so it's the same. But the other one is a weak base. A weak base. This weak base here, methylamine, we have to know how it dissociates when it's placed in water? How does the weak base dissociate when it's placed in water? And this is the answer. We said that the strong bases dissociate completely and water or hydroxide is formed, but a weak base, it produces hydroxide by interacting with the water molecule and pulling off the hydrogen. So if they say that CH3NH2 is a weak base, then what we have to show is that CH3NH2 grabbing a hydrogen from here, the water molecule, to produce the hydroxide ion, and what's left over is the CH3NH3 with a positive charge. Okay, very good. So that is our dissociation of a weak base. Now, let's draw the dissociation of a weak acid. The dissociation of a weak acid. A weak acid dissociates by writing the acid, HNO2, and what are the dissociative products going to be?
The hydrogen.
Yes, H plus and
the hydrogen.
And
NO2. What's the charge on the NO2?
NO2.
Minus. Very good.
It's a minus.
And now, because it said it was a
Negative.
weak acid, there's one more thing we do. Do you remember? What do we do?
Yeah.
Wait, this is a weak acid?
Yeah.
Oh, wait, this is a weak
And so we
acid?
just draw a second arrow
That's right.
to show that these two can come back together and form that product,
Okay.
or that starting material, right?
And that's something we don't do with the weak base.
And that's something we don't do with the
We do
weak
that with the
base.
weak base as well. We should have. Very good. All right. Now our strong acid, HClO3, chloric acid, HClO3. What are our dissociative products again?
Okay, H. This is
Okay,
gonna be a weak
H.
acid.
Oh, whoops.
So
This is
No,
going
it's
to be a
not.
weak
It says right there,
acid.
strong acid,
So-
right? Strong acid.
okay.
So I should have just wrote one arrow. Okay?
Oh, okay.
H with a positive charge, right? And what?
Okay, so H,
And then
right,
COO3,
and then COO3,
and that's going to be a negative charge.
Very good.
and that's going to
Excellent.
be a negative charge.
Now, can you see how on the slide they've written it slightly differently?
okay.
Can you tell me what the difference is between the last two that we did on the slide and the last two that we did on the paper?
Well, I see
Um,
where, they did.
Well, I see where, they did put in the,
Aqueous, I can't quite read that.
Oh, yes. Uh-huh.
is that aqueous? I can't quite read the,
And
and,
Well, the big thing that they did here is they
point this out to me.
included the water molecule.
yeah, point this
Right,
out
you see
to
that?
me.
Oh, I see. Oh, I see.
That's not necessary,
Oh, I
but if you
see.
do that,
Oh,
then
I
over
see.
here, you're going to have the H3O plus ion. And sometimes in tests, you'll see people write questions with this sort of a dissociative model, so you need to make sure that you're not uncomfortable with that water molecule there. Okay? All right, so the last one here is a strong base. It's strontium hydroxide, SrOH2. Strontium hydroxide. Well, it's going to be SrOH2. Strong, so it's going to completely dissociate. What are the resulting ions going to be?
So, you said it's a strong base.
So,
So it's
You said it's a strong base,
plus
so it's
Strontium
Sr plus,
plus, like that.
plus, and then
yeah,
plus
strontium plus,
that.
and then plus after that.
Now, will we balance this and say 2 OH?
That's right.
Now, will
Need
we
two
balance this and say 2
hydroxide
OH?
ions, right? There's one other thing that we're missing.
And then we're
Okay.
missing.
And then we're missing,
Well, you just need a
we would have to
+2
have
charge
2
on the strontium,
plus 2, right?
because strontium is a +2 ion.
Or +2, right.
Okay,
got
very
it,
good.
got it.
So this slide here shows us the dissociation of a weak base, a weak acid, strong acid, and a strong base. Okay, very good. Now, we talked a while back about how our general reaction form so far is this AB plus CD forming AD plus CB, and how AB and CD represent aqueous ionic compounds, and how one of these generally is going to be a solid if it's a precipitate reaction. Precipitate reaction. A reaction will occur if the combination of the ions that are here, remember these are aqueous, and so they are all dissociated in water. A reaction will occur if a combination of these forms a solid, right? Now, there is,
Right.
here's an example here, sodium sulfate and barium chloride combined together, and the product is sodium chloride. See how the cation here goes with the anion there, and the barium sulfate. And because barium sulfate is insoluble, this is a precipitate reaction. A reaction will also occur if an acid reacts with a base. Because when an acid reacts with a base, then you have HCl, for example, combining with sodium hydroxide, a base. The same pattern, can you see how we have A, B, that's H and Cl, C, D, sodium and the hydroxide ion, and then they switch places, right? The sodium comes with the chloride ion, and the hydrogen goes with the hydroxide ion, but the hydrogen and the hydroxide ion don't form a compound HOH, they form H2O. Can you see that?
And the NaCl, that's a,
Yeah.
that's still
And the NaCl, that's still
NaCl?
that's not solid, right?
That's right.
That's a,
It's not solid. NaCl is
Yeah.
aqueous. But water here, which didn't exist before,
okay.
water is not aqueous. It's
Yeah.
liquid, right? So this is a chemical reaction because the chemistry is different. We had these ions floating around. The hydrogen ion and the hydroxide ion found each other and formed a water molecule. All right, so this is an acid reacting with the base. We can call this sort of reaction a acid-base reaction, or you could call it a neutralization reaction. That's fine too. And then another kind of reaction that we have that follows this pattern is where a weak electrolyte is formed from two strong electrolytes. Now that doesn't happen very often in our class. It happens in nature, that happens, but I mean in class we don't talk a lot about this example. And another example is when a gas is formed when we mix reactants together. And we talk less about this, but we do have to kind of be aware of it. That our fourth way of kind of identifying a reaction has occurred is if a gas forms. So we have our insoluble product, or our precipitate, our acid and base, or our neutralization reaction, a weak electrolyte product, or gas forming as a product. All right? So, let's look at some of these reactants. All right? They all follow this pattern where the cations change partners and the result is two new compounds. But if the two new compounds that are going to form aren't insoluble, if one of them is not insoluble, if one of them is not water, if one of them is not gas or a weak electrolyte, then we say the reaction won't occur. The reaction won't occur. Because essentially what we'll have is the reactants and the products all broken up into their ions, and we'll have them all cross out, and so there will be no net ionic reaction. Okay? Net ionic equation. So, we can look at the reactants, their cations and their anions, switch the cations with the anions, make sure that we have a balanced reaction, and then see if we have a precipitate. Now, how do you think we're going to be able to know if one of the products we form is a precipitate?
Isn't one of them
well, they could be
polyatomic
polyatomic ions,
ions?
but
Or
yeah.
in
How
that,
are we going to know though if it's a
precipitation
precipitate? Do you have any ideas?
or not?
Well, we can use this, right?
Okay, no, I don't.
It's our solubility table. Right? Yeah, so we'll be able to use that and predict whether or not the products will be insoluble. We can predict whether or not water will form by looking and seeing if one is an acid and one is a base. Okay? And there's our solubility table again for reference. So, let's review our solubility table real quick with these compounds here.
Okay.
Are either of these soluble or insoluble? What do you think? The first one?
C2H2, that's
Very good. The
and
acetate
O2,
ion is always
that's
soluble. So calcium acetate is soluble. Good. What about iron carbonate? Iron 2 carbonate.
That's soluble.
So,
Iron
yeah,
carbonate?
that's soluble.
Oh, wait, I guess I'm looking at.
Oh wait, I guess I'm looking at C.
Well, the carbonate. That's CO3.
Well, the carbonate.
Yeah, CO3 2 minus.
That's CO3, right?
Yeah, isn't that soluble?
Is that what rule are you looking
Yeah,
at?
isn't that soluble?
Look at number 2.
Rule number 2?
I'm looking at number 2.
Okay, so rule number 2 talks about the ammonium ion, the nitrate, the perchlorate, chlorate, and acetate. But the carbonate is not in rule number 2. The carbonate is in...
That's not carbonate?
No. Carbonate is CO3 2
that's not
minus, and it's in
carbonate?
rule number 6.
Oh, thank you.
Oh, thank you.
Okay, so then it's insoluble.
Okay.
Very good.
So
Very good.
then
Insoluble.
it's insoluble.
How about the last one?
GCL.
Tell me the rule also.
So I'm looking at number 3.
Mm-hmm.
So I'm looking
Okay,
at
yeah.
number 3.
Good.
And so the Cl minus.
And
that's
so the Cl
All right.
except-
minus,
well,
that's a soluble.
combined with-
Except when combined with
Okay.
Ag,
So
right?
what are we saying? Yes or no?
So we're saying no.
No, not soluble.
So we're saying
Very
no.
good. Excellent. So we know how to use the solubility rules. So now we can predict whether or not this reaction will occur based on either a insoluble product, acid and base combining to form water, or a gas forming reaction. Actually, we're not going to have any gas forming reactions in this slide or any of our practice problems for now. So let's look at this and see if we can see that an insoluble product will occur or if water will form, if it's an acid-base reaction. What do you think?
Well,
Can you predict our products for us?
So we're going to combine
so
PB
so we're
Yep.
going to combine PB
Lead.
with
um,
OH
sorry,
With the hydroxide ion. Good.
with OH.
So lead hydroxide.
and then NO with
And then
or CA
NO with C or Ca calcium
Very good.
NO3 whatever.
Yes.
Calcium nitrate. And then
So now we have to see if it's soluble.
okay, so now we have to see if it's soluble.
Yep.
Write that down.
Let's
insoluble,
also
right?
write down the
After we write
products
that
for this
down?
reaction first. So
Okay, that's okay.
you said that PB.
Okay, that's okay.
Now what's the charge
Yeah.
on the PB ion?
Yeah. Um
Okay, let me look here.
okay, let me look here.
It's
It's a
positive.
positive.
Yeah, we
Three?
can't tell, can we? Because of its
Can't
location
quite
on the
make it out.
periodic
What's
table.
that question mark?
Well, it's not a question mark. It's
What's that
just
question mark?
it's a post-transition metal.
I'm looking at row 4.
I'm looking at
yeah.
row 4.
Uh-huh, that's right. But because it's a post-transition metal down there, it's
Oh,
to be we can't predict based on its location on the
Oh,
periodic
okay.
table.
row 4 doesn't because we don't know what the
So at this point, row
Nope,
4
we're
doesn't
gonna have to use-
apply because we don't know what the
We're going to have
charge
to
is.
use its counter
We
ion
don't know how many
to
plus,
find
right?
out what its charge is on it.
okay, which is
Okay.
CaOH, right?
No,
Uh,
the nitrate, the NO3,
Okay, which is
with it.
C8OH, right?
Does that make
I
sense?
see.
Yeah. So what's the charge on the nitrate?
Oh, I see.
That's a polyatomic ion.
Uh,
Yeah, yeah. And that's NO3.
Yes.
So
Yeah.
that's negative.
yeah.
Very good.
And
Negative
that's
1.
NO3. So
And how many
that's
of those
negative.
nitrates are with the lead ion in the compound?
Well, I see the 3 inside.
Well,
outside the parentheses.
I see the 3 inside. Well,
That's a
2,
2.
but outside
That's a
the
2.
parentheses,
That's a 2.
is that a 3 or 2?
2 minus 2.
That's a 2.
2
Okay,
minuses. And
then
so the lead
2
must be a what?
minus 2.
Positive 2.
Positive 2. Very good. So the
Positive
lead
2.
ion is going to come together with what on the other side?
So the lead iron, PB.
So
Yep, lead ion,
the lead iron,
lead 2,
PB, PB2 is going
OH.
to,
Now what's the charge on the OH?
yeah, that's coming together with the OH.
Yeah, that's negative.
Negative 1. All right. So
Yeah,
how are they
that's
going to come
negative
together?
Ion.
So it
I'm
would
sorry,
be
negative.
PB.
Uh-huh.
So it would be
PB2.
PB plus, well, PB2OH. I'm
Just
sorry,
a 2 like that, right?
PBOH negative 2.
That's right. And so we also want to show that we
How am I doing
got the
that? That's
2
right.
hydroxide ions, right?
Okay, that's where we're balancing.
Mm-hmm.
Okay, that's
Okay,
where
very
we're
good. So we got
balancing.
it. So now we can look
right.
on our solubility table and see if lead hydroxide is soluble or insoluble.
And that's on,
Okay, yeah. and that's on 3.
I think it's rule 5.
Well, let's see.
I think it's rule 5.
PB number 3. Well, you're looking on 5.
Well,
What was
it
it
does
look
talk
on
about
3? I guess
PB with chloride
Okay,
and
so
bromide
5
and
all
iodide
metal
on 3.
hydroxide.
But here we don't have that. We have the hydroxide. So 5 is the hydroxide.
Oh, I see. Okay.
So,
Okay. So,
Except what?
yeah, they're all, it's insoluble. Except when
With
combined
group
with
1A, calcium,
carbon.
strontium, or barium. Okay, very good. So it is going to be
calcium.
insoluble,
Yeah.
solid, right? So we know that that is going to be a precipitation reaction, right?
I'm sorry, you said that last part again?
Well, because we've identified that lead hydroxide
I'm
is
sorry,
a
you said that
solid,
last part again?
then we know that this reaction is going to be a precipitate reaction.
Okay.
Now, can we
Particip-
predict what the
yeah.
other product will be?
Right.
Well, so I was under the impression that the other products
Well,
would just be.
So I was under the impression that the other products
They
would
might
just
be. They might be, but we
uh,
don't know until we
we have
predict
to
them.
go
spectators.
Okay, so it would be CB.
Oh, but we have to go ahead and,
Calcium.
okay, so it would be CB, so
And then
calcium,
I forgot what NO is.
NO3 is nitrate.
and then I forgot what NO
You remember the
is.
charge on the nitrate?
Yeah.
Nitrate,
Well,
that's right.
I have to look it up.
Yeah, well,
It's,
I have to look
it's
it up.
-1.
Very good. What's the charge on the calcium ion?
it's a -1.
And calcium. Yeah. Is
And calcium, yeah, is a,
it's a +2.
+2. Very good.
is a +2.
So,
Okay, so we need to balance these.
Okay, so we need to balance these.
what is it going to be?
So it would be
So it would be,
CA.
well,
And
CA
and then
and
parentheses.
then NO3
we would put 2.
and then
Very good.
parentheses.
Excellent. So is
It would
that
put 2
soluble? Is
down
that going to
there.
be a solid, or is it going to be insoluble? Sorry, it's going to be insoluble, solid, or is it going to be soluble, aqueous?
Okay.
Wasn't there a rule about column 2?
Wasn't there a rule about
I think there's a
column
rule
2?
about nitrate. I think rule 2 about nitrate.
Okay.
Yeah, there's the rule on nitrate.
Yeah,
Okay,
there's
so
the
with
rule on nitrate.
it's soluble.
Very good.
Okay,
Aqueous.
so with the rule
soluble.
on nitrate, it's soluble.
So we can write down those products, a calcium nitrate and a lead 2 hydroxide. And the lead 2 hydroxide is solid. So yes, this is a precipitate reaction.
Okay, so then the CaNO3, that's not going to be.
Okay, so then the
It is,
CaNO3, that's
It is going to be a spectator ion
bystander.
because it's aqueous.
Or
right?
spectator, I mean.
So the nitrate, yeah, the nitrate and the calcium are the
Because it
calcium
is
was
aqueous.
aqueous on the
Okay.
left, and the calcium is aqueous on the right. The nitrate was aqueous on the left, and the nitrate is aqueous on the right. So the net ionic equation here is just going to be this one down here, where the lead combines with 2 hydroxides to form the lead hydroxide. Very good. That's a good job for today. Next time we'll go over a couple more of these reactions and predict whether they'll form products or not. Okay?